Hi guys, Sauce here. Pre-calculus content lesson called Features of Rational Functions, Asymptotes and Wholes. We're going to take a look at a couple of functions. I'm writing x squared plus 5x plus 6, all divided by x plus 1. And I'll be comparing that to another function that's very similar, x squared plus 5x plus 6, all divided by x plus 2. These two functions are the same type. They're rational functions. That means they are a function divided by another function. And the numerators of both of these rational functions are the same, x squared plus 5x plus 6, but their denominators are slightly different. X plus 1 in this case, x plus 2 in the other. These functions look very similar. If we were to graph them, we would see quite a difference. On a graphing calculator, you could graph these by hand. It would be time-consuming and tedious, but possible, making a t-table and plotting points. You can also graph it on other types of software and calculators, but on this TI Inspire, we have one of the functions in blue, which has two branches much like a hyperbola. They're curved, and we have the other function in red, looks like a straight line. The function that looks like a straight line, I will sketch right above the function. It's the one that has a denominator x plus 2, and it looks approximately like this. The one that looks like a transformed hyperbola, I will sketch above it. And it has a curve like this, and another one, let's get it approximately like so. So these functions are very similar, slight difference in the denominator, very significant difference in their graphs. So how would we be able to tell that without a graph? And how can we show algebraically what these graphs are going to be like and what features are on this graph in a curve? We have a discontinuity, and there's something about the feature of this graph that makes it look like a line, but it's not quite a line. We're going to manipulate both of these algebraically. We're going to take the numerator of each, and we're going to factor it. Whatever factoring technique you prefer, using the quadratic formula, guess and check, the factored form of both, because they're both the same, is two factors, two binomials, x plus 2 times x plus 3. You can confirm that if I redistribute and multiply the x plus 2 factor and the x plus 3 factor, it will recreate the distributed form that we started with. I'm going to put parentheses around my denominator to make it look like a grouped factor above. And in the other function, I have the same factored form in the numerator, but the denominator I'm going to group as an x plus 2. When we've factored, you might be able to see where the difference in the graphs is going to come from. In this first equation, this first function here, I have three factors, and they're all different. However, in this function, two of the factors, one in the numerator and denominator, are equal. They're the same factors, and they can be canceled out. In this second function here, it is equivalent to x plus 3. So, what features of the graph are now possibly more able to be seen if we are clear on what the algebraic simplification is? This function here, x plus 3, looks like a line in the graph because the equation x plus 3 is a linear equation. We have a slope of 1, we have a y-intercept of 3. That is approximately captured in this graph here. In the original that didn't get simplified, we didn't cancel out a common factor, we still have a problem that we've always had all along. that if I were to put -1 into the function, if I replace x with -1, in the denominator I'm going to get a -1 plus a +1, which means that the denominator will be 0. The denominator is still 0, even if it's in factored form. And look to the graph. We have a discontinuity, and that discontinuity is at an x value of -1. The graph shows us that the function isn't defined at -1. We have a vertical asymptote there, hopefully easily seen by how these branches diverge from one another. So we could say formally that we have the function is undefined at x equals -1, and specifically the feature of the graph that this value at x equals -1 makes on the graph is called an asymptote. It's a vertical asymptote, and that asymptote is at x equals -1. We don't have an asymptote in this other function. We do have a problematic value. This function, the second one, is undefined at x equals -2. Because if we put -2 in for x in the original function, we'll get 0 in the denominator. But that didn't create a vertical asymptote in the graph, as we can see, because this problematic x plus 2 got canceled out when we put it in factored form and simplified what we had left to x plus 3, which creates the line. But the original function is still undefined at x equals -2. It just has a different feature. Our graphing calculator, or any technology, is incapable of showing you what's happening on this line at x equals -2. There's no asymptote. We can't see it on a calculator, but if we were to zoom in and keep zooming in at some place at -2 on the function, then what we'd see is a hole, a place on the line that is empty because there cannot be any value at x equals -2. It causes the division by 0 error, but it doesn't do it in such a way that creates an asymptote. It does it in such a way that creates a hole because that problematic piece can be factored out. Unlike the function that can't be factored, produced an asymptote. To finish up, we could say that this function is undefined at x equals -2, but the feature that you will find there is a hole at x equals -2. And the reason why this is something that a human needs to be aware of is because the calculator screens are incapable of being able to show a continuous line with an infinitely small hole at any value. We have to be able to find it in the process of the reasoning.